What if everything we think we know about the universe is backward? For nearly a century, scientists have told us the cosmos is expanding, galaxies racing away from each other, space itself stretching like an infinite balloon. But what if that's only half the story? What if, hidden in the fabric of reality, the universe is actually contracting, quietly collapsing in on itself, while we're none the wiser? This isn't just science fiction, it's a real theory gaining traction among some of the brightest minds in physics. Welcome to the mind-bending idea of the Great Reversal, a cosmic sleight of hand that could rewrite the destiny of everything. Think about the night sky, those countless stars, the distant galaxies, all seemingly drifting apart. It's a vision of endless growth, a universe forever pushing outward. But beneath that illusion, there might be something far stranger at work. Imagine dark energy, the mysterious force driving expansion, suddenly flipping its role. What if it's not pushing space apart but pulling it together, like a cosmic rubber band snapping back? The implications are staggering. Galaxies might not be racing away, they could be falling toward us, their light stretched and twisted to look like expansion. Time itself might be playing tricks on us, hiding the truth in plain sight. This isn't just about rewriting textbooks, it's about unraveling the very fabric of reality. If the universe is contracting, what happens to the future? Could black holes merge faster? Would time eventually run backward? And most haunting of all, how would we even know? Today, we're diving into one of cosmology's most radical ideas, exploring the science, the skeptics, and the startling evidence that could upend our understanding of existence. From the secrets of dark energy to the fate of distant galaxies, this journey will challenge everything you thought you knew. So buckle up, we're about to question the universe itself. The idea of an expanding universe didn't always seem obvious. In fact, for centuries, astronomers assumed the cosmos was static, unchanging, and eternal. That all shifted in the 1920s when Edwin Hubble peered through his telescope and noticed something bizarre. Distant galaxies weren't just sitting still, their light was stretched, shifted toward the red end of the spectrum. This redshift meant they were moving away from us, and the farther they were, the faster they raced into the void. Hubble's discovery shattered old beliefs, revealing a universe in motion, ballooning outward in every direction. But what made this expansion even more puzzling was its source. For decades, scientists assumed gravity would eventually slow the universe's growth, pulling everything back together in a so-called Big Crunch. Then, in the late 1990s, two teams studying distant supernova made a jaw-dropping find. Not only was the universe expanding, it was speeding up. Some invisible force, later dubbed dark energy, was overpowering gravity, pushing galaxies apart faster and faster. This discovery cemented the Big Bang as our leading cosmic origin story, with dark energy as its mysterious accelerator. Yet here's where things get really strange. Dark energy isn't just a constant push, it's a wild card. Some theories suggest its strength could change over time. What if, instead of driving eternal expansion, it weakens or even flips? Picture a roller coaster climbing a hill, powered by dark energy. Right now, we're racing upward, but if that energy fades or reverses, the ride could plunge back down. The universe wouldn't just slow, it could collapse, galaxies rushing toward each other like a cosmic game of reverse dominoes. The evidence for expansion is strong, but science thrives on questioning the obvious. Redshift, for example, might not be the full story. Could light from distant galaxies be stretched not by expansion, but by some other cosmic trick? And if dark energy isn't as uniform as we think, could patches of the universe already be contracting while the rest expands? These aren't just thought experiments, they're real possibilities some physicists are exploring. The expanding universe paradigm is our best model, but science is built on rewriting old truths. After all, history shows us the cosmos always has surprises up its sleeve. Dark energy is the universe's greatest unsolved mystery, a force so baffling, it makes up nearly 70% of everything in existence, yet we still don't know what it actually is. Right now, it acts like an anti-gravity, pushing space apart faster and faster. But what if that's not its only trick? The key lies in something called its equation of state, a fancy term for how its density and pressure interact over time. In the simplest models, dark energy stays constant, relentlessly driving expansion. But nature rarely sticks to the simplest script. Some theories suggest dark energy could evolve, growing stronger or weaker as the cosmos ages. Imagine it as a dimmer switch, not just an on-off button. If its pressure shifts from negative to positive, if it flips from repelling to attracting, the universe's fate changes overnight. Instead of endless expansion, space might start shrinking like a breath exhaled after a deep inhale. Galaxies would slow their outward rush, pause, then begin falling back toward each other. The redshift we see today could one day reverse into a blue shift, with distant starlight compressing as space itself contracts. But how would we notice such a reversal? At first, probably not at all. The change would be subtle, hidden in the faintest distortions of light from the farthest galaxies. Over billions of years, though, the effects would snowball. Stars might appear brighter as their light gets squeezed, and the cosmic microwave background, the afterglow of the Big Bang, could show strange new patterns. Even Time's arrow might behave differently in a contracting universe, though that's a puzzle even physicists are still untangling. The real twist, we might already be inside this reversal without realizing it. If dark energy's shift began recently on a cosmic timescale, the earliest signs could be buried in data we've yet to decode. It's like standing on a beach, watching the tide creep in. You don't notice the water's rise until it's lapping at your feet. For now, telescopes scan the skies for clues, hunting for anomalies in supernova or galaxy clusters that don't fit the standard expansion story. Every flicker of unexpected data could be a whisper of the cosmos turning inward. And here's where it gets truly wild. If contraction is real, it might not happen evenly. Some regions of space could collapse faster than others, creating cosmic pockets where gravity takes over while the rest of the universe still expands. Picture a sinking ship with some cabins flooding first, except in this case, the ship is space-time itself. The universe we think we know might be far more fractured, more dynamic than we ever imagined. So what's next? The hunt for answers is on. From next-generation telescopes to advanced simulations, scientists are probing dark energy's secrets like never before. Whether it's a constant force or a shape-shifting phantom, one thing's clear: the story of our universe is still being written, and the next chapter could defy everything we thought was true. Before dark energy rewrote the cosmic rulebook, there was another ending in mind for our universe, one where gravity gets the last laugh. The Big Crunch hypothesis paints a dramatic finale, galaxies slowing, reversing course, and eventually smashing together in a fiery collapse. Picture the Big Bang playing in reverse space, shrinking, temperatures soaring, all matter hurtling toward a single point of infinite density. It's the ultimate cosmic reset button, a singularity mirroring how everything began. For decades, this idea seemed plausible. After all, gravity is relentless. It binds planets to stars, stars to galaxies, and galaxies to clusters. If the universe had enough matter, its collective pull might eventually overcome expansion's momentum. But then dark energy entered the scene, flinging galaxies apart faster than gravity could reel them in. The Big Crunch fell out of favor, dismissed as a relic of an older, simpler cosmology. Yet science has a way of circling back. New research suggests the crunch might not be so dead, just hiding in plain sight. Modern theories propose that dark energy isn't necessarily a one-way force. Instead, it could behave like a cosmic pendulum, swinging from repulsion to attraction under the right conditions. Some models even suggest that what we perceive as accelerated expansion might be an illusion, a temporary phase before the pendulum swings back. Here's where it gets eerie. If contraction began today, we wouldn't feel it, not yet. Space is so vast that even at light speed, the effects would take eons to reach us. By the time nearby galaxies started blue-shifting, humanity, if it still exists, might be living on borrowed time. The sky would slowly brighten as distant starlight compresses, temperatures rising until the cosmos becomes a pressure cooker. Stars would collide, black holes merge, and space-time itself might warp under the strain. But the Big Crunch isn't the only way the universe might contract. Some physicists speculate about a quieter collapse, one where dark energy weakens just enough for gravity to take over in pockets, creating isolated regions of contraction amid an otherwise expanding cosmos. Imagine bubbles of reverse expansion floating in a sea of stretching space. We could be inside one right now, none the wiser. The real question isn't just whether the universe can contract, but how it would happen. Would it be a uniform collapse or a chaotic, piecemeal implosion? Could time itself behave differently in a shrinking universe? And most hauntingly, if the cosmos is already contracting somewhere, how would we ever know? The answers might lie in the faintest anomalies, galaxies moving slightly wrong, light bending oddly, or shadows in the cosmic microwave background where none should be. What makes this more than a thought experiment is the data. Recent observations of supernova and galaxy clusters have revealed tiny discrepancies, hints that dark energy's behavior might not be as uniform as we thought. Whether these are statistical flukes or whispers of a coming reversal, scientists are racing to find out, because if the universe is turning inward, even slowly, it changes everything, not just our future, but our understanding of reality itself. So while the Big Crunch might sound like an old idea, it's far from obsolete. In science, the past often returns with new layers, new complexities. And in a universe full of mysteries, sometimes the most radical idea isn't inventing a new story, but realizing the old one wasn't wrong, just incomplete. What if the universe is already collapsing and we just haven't noticed? The cosmic microwave background, that faint glow from the dawn of time, might be hiding the first clues. Scientists have long studied its subtle ripples, the fingerprints of the early universe's density variations. But some of those ripples don't quite fit the standard models. Tiny, unexplained cold spots, regions slightly cooler than they should be, could be more than random fluctuations. Could they be scars from pockets of space where contraction has already begun? It's like finding cracks in a frozen lake. They might hint at shifts happening beneath the surface. Then there's the mystery of galaxy clusters moving in ways that defy expectations. Some appear to be drifting toward each other faster than gravity alone can explain, as if tugged by an invisible current. Astronomers call this dark flow, a controversial but tantalizing observation. If real, it might suggest vast regions of space are being pulled toward something beyond the observable universe, or perhaps toward each other in a slow-motion collapse. Imagine tossing confetti into the wind, only to watch some pieces suddenly reverse direction. That's the kind of anomaly researchers are trying to decode. Even the expansion rate itself is under scrutiny. Measurements of how fast the universe grows, the Hubble constant, don't always agree. Some methods, like tracking distant supernova, give one answer. Others, like mapping the cosmic microwave background, give another. This Hubble tension might just be a calibration issue, or it could be a sign that expansion isn't uniform. If dark energy's push is weakening in certain areas, those regions might already be transitioning to contraction, subtly skewing our measurements, the most haunting possibility. We might be looking at the universe through a funhouse mirror. Light from distant galaxies could be distorted not just by expansion, but by hidden regions of collapsing space bending its path. Gravitational lensing, where massive objects warp light, is well documented. But what if some of those lenses aren't just galaxies or black holes? What if they're folds in space-time itself, creases where the fabric of the cosmos is buckling inward? For now, these anomalies remain on the fringe, tantalizing but unconfirmed. Yet science advances by chasing the unexplained. Every odd data point, every stubborn discrepancy, could be a breadcrumb leading to a deeper truth. The universe doesn't owe us simplicity. It might just be far stranger, far more dynamic than we've dared to imagine. At the smallest scales of reality, the universe behaves in ways that defy common sense. Empty space, far from being a static void, is a seething ocean of quantum fluctuations, particles popping in and out of existence so fast they barely leave a trace. These fleeting disturbances might seem insignificant, but what if they're secretly shaping the fate of the cosmos? Quantum mechanics tells us that even in a perfect vacuum, energy never sits still. Virtual particles emerge, collide, and vanish in fractions of a second, creating a microscopic dance of creation and destruction. It's like watching a pot of water simmer. Bubbles form and burst unpredictably, each one a tiny rebellion against stillness. Now imagine those quantum bubbles don't just vanish. What if, under the right conditions, they leave behind faint imprints on the fabric of space-time? Some theories suggest these fluctuations could accumulate over eons, subtly altering the behavior of dark energy or even gravity itself. Picture a snowball rolling downhill, gathering mass, except here, the snowball is space-time and the flakes are quantum ripples. Over billions of years, these tiny nudges might add up to something far grander, a shift in the universe's very expansion. The math behind this idea is dizzying. Quantum fields permeate all of space, and their fluctuations are woven into the equations governing cosmic evolution. If certain fields decay or transition to lower energy states, a process called quantum tunneling, they could trigger a phase change in the universe itself. Think of it like water freezing into ice. The molecules rearrange and suddenly the rules change. In cosmic terms, such a shift might flip dark energy from a force of expansion to one of contraction, all because of microscopic instabilities bubbling up from the quantum foam. But how would we detect such a stealthy reversal? The clues might lie in the oldest light we can see, the cosmic microwave background. Quantum fluctuations from the universe's first moments are frozen into this radiation as slight variations in temperature. If those patterns show unexpected twists, strange asymmetries, or anomalies in polarization, they could hint at quantum effects nudging the cosmos toward collapse. Even more intriguing, certain particle collisions in accelerators might reveal hidden properties of quantum fields that point to this instability. It's like finding cracks in a foundation. They start small, but they can bring down a building. The wildest part, quantum fluctuations might not act uniformly. Some regions of space could experience stronger effects, creating pockets where contraction begins earlier. This could explain oddities like dark flow or those mysterious cold spots in the cosmic microwave background. the universe wouldn't just contract, it would crumple, like a sheet of paper being crushed unevenly. And if we're inside one of those crumpling zones, the night sky's expansion might be an illusion, a local effect masking a far stranger truth. So while quantum mechanics often feels disconnected from the vastness of galaxies, it might hold the key to the universe's ultimate fate. From the tiniest flickers of energy to the grandest scales of existence, everything could be linked in ways we're only beginning to grasp. The more we probe these connections, the clearer it becomes. The cosmos doesn't play by separate rules for the small and the large. It's all one intricate system, and the answers to its biggest mysteries might lie in its smallest details. Time isn't just a one-way street. It might be a cosmic carousel, endlessly spinning between expansion and contraction. The idea of an eternal universe cycling through rebirth after rebirth isn't just poetic, it's rooted in a principle called time symmetry. Picture a pendulum swinging back and forth, never stopping. Now imagine that pendulum is the entire cosmos, with each swing representing a big bang followed by a big crunch. This isn't just fantasy. Some of the most respected equations in physics suggest time could work both ways, with no rule saying the universe must age in a single direction. Take Einstein's theory of general relativity, for example. The math doesn't care if time runs forward or backward. The equations hold up either way. It's only our everyday experience, the shattering of a glass, the graying of hair, that makes time feel like an arrow. But at the universe's grandest scales, that arrow might curve back on itself. If the cosmos collapses, could the laws of physics reverse, rewinding creation like a film played in reverse? Stars might unburn, galaxies unspiral, and eventually all matter could rush back into a singularity, priming the next Big Bang. The beauty of cyclic cosmology lies in its elegance. Instead of a single, lonely universe with a definitive beginning and end, we get an endless symphony of creation and destruction. Hindu cosmology called this idea the kalpa, a cycle lasting billions of years. Modern physics frames it with equations, but the core concept is eerily similar. Universes breathing in and out, each one a new verse in an infinite cosmic poem. Yet skeptics ask, where's the proof? If the universe has cycled before, shouldn't there be scars from past iterations? Some researchers hunt for those fingerprints in the cosmic microwave background, searching for concentric rings or anomalies that might hint at collisions with a pre-Big Bang universe. Others argue that black holes, those cosmic vacuum cleaners, could be recycling matter and energy across cycles, their singularities birthing new universes in their depths. It's a wild idea, every black hole a doorway not to oblivion but to a fresh cosmos. The most tantalizing clue might lie in dark matter. If some of it survived previous cycles, lingering like cosmic leftovers, its distribution today could reveal whispers of a universe that came before ours. Imagine finding a fossil embedded in the sky, not of ancient life, but of an ancient cosmos. Of course, cyclic models aren't without flaws. The second law of thermodynamics insists entropy, disorder always increases, making a perfect reset seem impossible. Yet some theorists propose that in a contracting phase, entropy could reset at the singularity, like a computer rebooting. Others suggest our universe is just one bubble in a vast multiverse, each with its own cycle independent of the rest. Whether the cycles are pristine or messy, the implications are staggering. It means the stars we see might have burned countless times before. The atoms in our bodies could have been part of galaxies in a prior universe. And if time truly is symmetric, then somewhere in the vast weave of existence, all of this has already happened and will happen again. The universe might not just be contracting in secret. It could be rehearsing for an encore, black holes aren't just cosmic vacuum cleaners, they might be the hidden architects of a collapsing universe. Picture them as gravitational anchors, their immense pull not just bending space-time but actively gathering matter into dense knots. As these monsters feed, they grow larger, their influence spreading like invisible roots through the fabric of reality. Now imagine a universe where black holes aren't just passive objects but active players in a grand reversal, their collective gravity weaving a web that could one day drag everything back together. The math behind this is staggering. Black holes don't just sit still, they merge, collide, and devour, creating ever larger singularities. Over trillions of years, this process could turn the cosmos into a network of supermassive black holes, each pulling on the others like magnets. If dark energy weakens, these gravitational titans might become the dominant force, slowing expansion and eventually reversing it. It's like a cosmic game of tug-of-war where the black holes, once outmatched, finally start winning. But here's the twist. Black holes might not just wait for contraction to happen. They could trigger it. Some theories suggest that as black holes evaporate over unimaginable timescales, they release energy in ways that destabilize dark energy. Others propose that the singularity at a black hole's core could be a doorway to a new phase of the universe, where matter and energy are recycled into the next cosmic cycle. Imagine pouring sand into an hourglass. The black holes could be the narrow point where everything flips, where the universe's expansion turns into contraction. The most chilling possibility, we might already see hints of this process. Galaxies with unusually active supermassive black holes at their centers sometimes show strange behavior. Jets of energy shooting out, or stars orbiting in ways that defy expectations. Could these be early signs of black holes gearing up for a larger role in cosmic collapse? Even the mysterious dark flow, where galaxy clusters drift in unison toward some unseen attractor, might point to black holes orchestrating a slow-motion implosion on scales we're only beginning to map. Yet black holes aren't just destroyers, they might also be creators. In some models, a collapsing universe doesn't end in oblivion but rebounds into a new Big Bang. The singularity at a black hole's heart could be the seed of the next cosmos, a cosmic phoenix rising from the ashes of the old. If true, the black holes we see today might not just be pulling the universe apart, they could be building the foundation for whatever comes next. So while we often think of black holes as the end of the story, they might be the middle. Their gravity could be the silent force shaping the universe's fate, hidden in plain sight. And if they are already at work pulling the strings of contraction, we might be living in the calm before the cosmic storm, a moment in time where the universe seems to expand, even as its darkest corners prepare to bring it all back home. Phantom energy sounds like something from a sci-fi nightmare, a force so destructive it could tear the universe apart atom by atom. But in cosmology, it's a real, albeit speculative, possibility. Unlike ordinary dark energy, which pushes space apart at a steady pace, phantom energy is far more sinister. Its density increases over time, meaning its repulsive force doesn't just persist, it grows exponentially stronger. Picture a car accelerator stuck in overdrive, hurtling faster and faster with no way to brake. Now imagine that car is space-time itself, and the accelerator is phantom energy, relentlessly stretching the cosmos until even atoms can't hold together. This apocalyptic scenario is called the Big Rip, where galaxies, stars, and eventually the fabric of reality are shredded into oblivion. But here's the twist: phantom energy might not always lead to a rip. Under certain conditions, it could flip the script entirely, triggering a collapse instead. How it all comes down to the equation of state, the relationship between phantom energy's pressure and density. If that relationship crosses a critical threshold, the repulsive force could transform into an attractive one, like a rubber band stretched too far suddenly snapping back. Instead of ripping the universe apart, phantom energy might yank it inward, reversing expansion in a cosmic game of tug-of-war. The implications are staggering. If phantom energy dominates, the universe's fate hinges on a razor's edge. One path leads to disintegration, the other to implosion, and the scariest part: we might not know which path we're on until it's too late. Phantom energy's effects would start subtly, hidden in the faintest distortions of light from the most distant galaxies. By the time the cosmos visibly changes course, the reversal could be unstoppable. Some models even suggest phantom energy could create a false vacuum decay, a bubble of collapsing spacetime that expands at the speed of light, rewriting the laws of physics as it spreads. Think of it like an ice crystal freezing a supercooled lake, but on a cosmic scale. One moment, the universe is expanding. The next, a wave of contraction sweeps through, erasing the old rules in an instant. Yet for all its terror, phantom energy remains hypothetical. No direct evidence proves its existence, but its potential is etched into the math of quantum field theory. If it's out there, lurking in the shadows of dark energy's mystery, it could rewrite not just our future, but our understanding of reality itself. The cosmos might be balancing on a knife's edge, and we're just beginning to glimpse the abyss below. Gravitational waves are the universe's whispers, ripples in spacetime sent across billions of years, carrying secrets from the most violent cosmic events. Since their first detection in 2015, these waves have revolutionized astronomy, letting us hear collisions of black holes and neutron stars. But what if they're also hiding clues to something even bigger, like the universe secretly contracting? The answer might lie not just in the waves we've detected, but in the ones we haven't. Imagine spacetime as a vast ocean. When massive objects like black holes collide, they create tsunamis, gravitational waves strong enough to ripple across the cosmos. But beneath those colossal waves, there could be subtler currents, faint tremors hinting at larger shifts in the fabric of reality. If the universe is contracting, even slightly, it might imprint a unique fingerprint on gravitational waves. Picture dropping a pebble into a pond while the water itself is slowly draining. The ripples would carry traces of that larger motion. Similarly, gravitational waves passing through a contracting cosmos could stretch or compress in unexpected ways, their frequencies subtly distorted by the grand reversal. The key to unlocking this mystery lies in next-generation detectors. Current observatories like LIGO and Virgo are marvels of engineering, but they're tuned to catch the loudest crashes in the universe: black hole mergers, neutron-star collisions. Future projects like the space-based LISA mission or the ultra-sensitive Einstein telescope will listen for fainter, lower-frequency waves. These could reveal patterns invisible to today's instruments, like a background hum of spacetime itself shifting. If contraction is happening, these detectors might catch gravitational waves that seem out of tune, their wavelengths stretched or squeezed in ways that defy standard expansion models. Even more intriguing are primordial gravitational waves, hypothetical ripples from the universe's earliest moments. If the cosmos has cycled through expansion and contraction before, these ancient waves could bear scars from previous collapses, like tree rings recording past seasons. Some theories suggest they might even carry echoes of a pre-Big Bang universe, a cosmic palindrome hidden in the static of spacetime. Detecting them would be like finding a fossilized ripple, a snapshot of a time before time. But gravitational waves aren't the only signals to watch. If contraction is real, it could warp the very geometry of spacetime. bending light in ways that create ghostly double images of distant galaxies or distorting the cosmic microwave background into strange, asymmetrical patterns. Future telescopes mapping the sky in unprecedented detail might spot these anomalies, piecing together a picture of space not just expanding but folding in on itself. The hunt for these signals is already underway. Scientists are refining models to predict how gravitational waves would behave in a contracting universe, while engineers push the limits of detection technology. Every new wave we catch could be a breadcrumb leading us closer to the truth, whether that's a cosmos forever expanding or one quietly turning inward. One thing's certain, the universe loves surprises. And if history's any guide, the biggest revelations often come from listening to the quietest voices in the dark. Entropy is the universe's silent dictator, the force that ensures disorder always increases, time always moves forward, and energy inevitably scatters into chaos. It's why ice melts, why coffee cools, and why the cosmos seems destined for a cold, dark fade known as heat death. But what if that's not the whole story? What if a contracting universe could bend or even break these thermodynamic rules? Imagine throwing a shattered glass into reverse, watching shards leap off the floor to reassemble in your hand. That's the kind of cosmic sleight of hand we're talking about. A universe where entropy doesn't just rise but might twist, flip, or reset entirely. At first glance, the idea seems impossible. The second law of thermodynamics is one of physics' most sacred principles. Entropy never decreases in a closed system. Yet a collapsing cosmos isn't just any system, it's space-time itself rewinding, galaxies hurtling backward, and the very fabric of reality tightening like a coiled spring. Under those extreme conditions, the rules might get flexible. Some theorists suggest that in contraction, gravity could become the dominant organizer, pulling matter and energy back into dense, ordered states. Picture a cosmic vacuum cleaner sucking scattered dust into neat piles, entropy decreasing not by magic, but by the sheer force of a universe falling inward. But here's where it gets stranger. Entropy isn't just about disorder, it's about possibilities. In an expanding universe, there's always more room for particles to spread out, creating more possible states, and thus higher entropy. But when space shrinks, those possibilities collapse. Particles are forced into closer quarters, reducing the number of ways they can arrange themselves. It's like stuffing an overpacked suitcase suddenly. There's only one way everything fits. This compression could effectively reset entropy, winding the cosmic clock backward toward order. The wild card, dark energy's role in all this. If it flips from repulsive to attractive during contraction, it might not just pull space together, it could rewrite how energy behaves. Quantum fields that once drove expansion might reconfigure, releasing stored energy in ways that locally reverse entropy. Think of it like a battery discharging in reverse, powering a temporary defiance of thermodynamic law. Certain regions of the universe could briefly become pockets of decreasing chaos, like eddies in a river flowing upstream, and then there's the fate of heat itself. In a contracting universe, the cosmic microwave background, the faint afterglow of the Big Bang wouldn't just fade, it would intensify. As space compresses, that primordial radiation gets squeezed, its wavelength shortening and energy rising. The cold void of space could grow warmer, stars might burn brighter in a shrinking sky, and the very concept of heat death could invert. Instead of a frozen end, the universe might face a fiery crunch, where temperatures soar toward infinity as everything collapses. But could entropy truly reverse or just transform? Some models propose that in a contracting phase, entropy doesn't vanish, it relocates. information and energy might funnel into microscopic structures like black holes or quantum knots in spacetime, preserving disorder in hidden dimensions. It's like sweeping dust under a rug. The mess is still there, just out of sight. If true, a collapsing universe could be far more complex than a simple rewinding tape. It might be a labyrinth of folded physics, where entropy's rules hold, just not where we can see them. The implications stretch beyond theory. If entropy can bend, it challenges our understanding of time's arrow. Would cause still precede effect in a contracting cosmos? Would memories unravel as the universe shrinks, or would consciousness somehow persist? These aren't just thought experiments, they're windows into whether the laws we take as absolute are truly universal, or just features of our current expanding era. For now, the thermodynamics of contraction remain a tantalizing puzzle, but with every new simulation, every tweak to quantum gravity models, we get closer to answers. The universe's end might not be written in cold, dispersing silence. It could be a roaring, chaotic reversal, where the rules we know are just the first verse in a much stranger song. String theory paints a universe far stranger than the three dimensions we experience every day. Imagine space isn't just length, width, and height, but a vast, folded landscape with hidden layers, like a book with pages we can't see. These extra dimensions, curled up at scales 1 billion times smaller than an atom, could hold the key to the universe's greatest mysteries, including this one. What if cosmic contraction isn't happening in our familiar dimensions at all, but in those hidden folds of reality? Think of it like a tree shedding leaves. From our perspective, the leaves simply vanish, but in truth, they're falling into a dimension we can't perceive. Similarly, the universe's expansion might appear unstoppable to us, while in higher dimensions, gravity or dark energy could be pulling space inward, like a hidden hand tugging on cosmic strings. String theory suggests that gravity, unlike other forces, isn't confined to our three-dimensional brain of existence. It leaks into these extra dimensions. If true, gravity's strength might not be constant. It could grow as the hidden dimensions contract, subtly shifting the balance between expansion and collapse. The math behind this idea is dizzying. In some models, the extra dimensions compactify, shrinking so tightly that their energy spills into our visible universe, altering the behavior of dark energy or even flipping its effects. Picture a balloon squeezed at one end. The air doesn't disappear, it rushes to the other side. If higher dimensions are collapsing, their air, the energy shaping space-time, might flood our dimension, triggering a reversal we're blind to. Even wilder, these dimensions might not be static. They could oscillate, expanding and contracting in cycles independent of our own universe's fate. If their rhythms sync up, the cascading effects could make entire galaxies behave as if they're falling toward us, when in reality, it's the hidden fabric of reality itself buckling and bending. So how would we detect such a hidden collapse? The clues might lie in gravity's quirks. If extra dimensions are tightening, gravity's strength in our universe could change over time, something telescopes might spot in the orbits of distant stars or the bending of light around galaxy clusters. Particle colliders like the Large Hadron Collider could also hunt for evidence, searching for exotic particles that briefly flicker into existence, relics of higher dimensional physics. Even gravitational waves, those ripples in space-time, might carry echoes of unseen dimensions if they vibrate in ways our models can't yet explain, the most mind-bending possibility. Our universe might not be alone on this higher dimensional stage. Other brains parallel three-dimensional worlds could float nearby in the bulk of hyperspace. If one of those brains began collapsing, its gravitational pull might distort ours, creating the illusion of expansion while reality is actually contracting. It's like two sheets of paper drifting apart on a windy day, except the wind is invisible and the papers are entire cosmos. For now, these ideas live at the frontier of theoretical physics, where equations outstrip experiments. But if higher dimensions are real, and if they're secretly shaping the universe's fate, then the greatest twist in cosmology might be this. The answers we seek aren't just hidden in distant galaxies or ancient light. They could be curled up right beside us in dimensions so small, so alien, we've yet to learn how to look. Quantum mechanics has always played by strange rules. Particles existing in multiple states until measured, waves collapsing into particles when observed. At the tiny scales of atoms, the observer effect is undeniable. The act of watching changes the game. But what if this quantum quirk isn't confined to microscopic realms? What if, on the grandest stage of all, the universe itself responds to being observed? It's a dizzying thought. That consciousness might not just witness cosmic expansion or contraction, but somehow nudge it. The idea isn't as far-fetched as it sounds. In quantum physics, reality seems to crystallize only when measured, as if particles wait for an audience before choosing their state. Some theorists, like physicist John Wheeler, took this further with the participatory universe hypothesis, a cosmos that requires observers to bring it into full existence. Extend that logic to cosmology, and the implications are staggering. If the universe's behavior depends on observation, could the presence of life, of conscious beings watching the stars, alter its trajectory? Imagine a cosmic feedback loop where intelligence, by merely existing, tilts the scales between expansion and collapse. Here's where it gets even wilder. Dark energy, that mysterious force driving the universe apart, might not be a fixed constant. Its strength could fluctuate based on quantum-level uncertainties, tiny probabilities that, when amplified across the cosmos, create ripples in spacetime itself. Now add observers to the mix. If consciousness collapses quantum probabilities, as some interpretations suggest, then life might indirectly shape how dark energy behaves. More observers could mean more measurements, locking dark energy into states that favor contraction over expansion, or vice versa. It's like a cosmic voting system where every conscious mind casts a ballot for the universe's fate. Critics argue this borders on philosophy, not physics. After all, how could something as fragile as human observation sway something as vast as the cosmos? But consider the numbers. The universe is old, nearly 14 billion years, and life, at least as we know it, is a recent blip. Yet in that blip, we've begun observing the universe in unprecedented detail, mapping galaxies, measuring dark energy, probing quantum fields. If observation plays a role, then the era of cosmic scrutiny we've entered might coincide with a shift in the universe's behavior, coincidence or connection. The wild card in all this is time. Quantum effects are instantaneous, but cosmic changes unfold over eons. If observers influence the universe's large-scale structure, would the effects appear immediately, or would they lag, like echoes across spacetime? Some models suggest that conscious observation could create quantum scars, subtle imprints in the fabric of reality that accumulate over millennia, slowly steering the cosmos toward contraction. Others propose that life itself might be a symptom of a universe poised for reversal, like canaries in a coal mine sensing an invisible shift. Of course, this isn't just about humans. Any conscious observers, aliens, artificial intelligence, even future forms of life we can't imagine, could contribute. The universe might not care who's watching, only that it's being watched. In this view, the rise of intelligence isn't an accident but a feature of cosmic evolution, a mechanism the universe uses to decide its own fate. For now, these ideas live at the edge of science, where physics meets metaphysics. But they raise profound questions. If the universe is truly participatory, then our place in it isn't just as spectators. We might be players in the grandest story ever told. Every telescope pointed at the heavens, every experiment probing quantum mysteries, could be more than passive observation. It might be the universe through us choosing what comes next. What if the universe isn't just collapsing? What if it's rebooting? Simulation theory, the idea that our reality might be an artificial construct, has long danced on the edges of science and philosophy. But if we're living in a cosmic computer program, could contraction be nothing more than a scheduled reset? Picture a video game reaching its memory limit. The system lags, glitches appear, and eventually, the only fix is to shut it down and start fresh. Now replace the game with the universe and the shutdown with a silent collapse. The implications are staggering. Every galaxy, every black hole, every conscious thought might just be lines of code awaiting deletion. This isn't just speculative fiction. Some versions of simulation theory suggest that an advanced civilization, perhaps a future iteration of humanity, could run universe-scale simulations to study their own origins. In that context, contraction might not be a physical process but a programmed endpoint, a way to recycle computational resources for the next simulation. Think of it like a cosmic Control-Alt-Delete, where the universe doesn't end in fire or ice but in a deliberate, elegant shutdown. The very laws of physics we consider immutable could be adjustable settings, with dark energy acting as a slider between expansion and collapse. But how would we know? Glitches might hold the answer. If our universe is a simulation, imperfections in its rendering could betray its artificial nature. Astronomers have already spotted oddities, particles with inexplicable energies, galaxies aligned in statistically improbable patterns, even the infamous axis of evil in the cosmic microwave background. These anomalies might just be cosmic noise, or they could be artifacts of a simulation straining under its own complexity. A contracting universe could amplify these glitches, like a computer struggling to process too many commands at once. Stars might flicker in ways physics can't explain, or black holes could exhibit behaviors that defy Einstein's equations, hints that the program is nearing its limits. The most unsettling possibility, contraction might not be the end but a loop. Simulations don't have to run once, they can be repeated, tweaked, and optimized. If our universe has collapsed before, evidence of past cycles could be hidden in the fabric of spacetime itself. Quantum fluctuations, those tiny jitters in empty space, might carry echoes of previous iterations, like fragments of corrupted data lingering after a reboot. Even the constants of nature, the speed of light, the strength of gravity, could vary slightly between cycles, adjusted by unseen programmers testing different parameters. Critics argue that simulation theory is untestable, more metaphysics than physics. But supporters counter that if the universe is a simulation, its creators would have left signatures, not just glitches, but deliberate clues. Contraction could be one of them. A simulated universe might not fade into heat death or rip apart. It could simply stop like a paused game, its code archived for future runs. The eerie fine-tuning of our cosmos, the precise balance of forces that allows life to exist, might not be luck but design. So where does that leave us? If contraction is a reset button pressed by some higher intelligence, then our search for cosmic truth takes on a new urgency. Every anomaly in the night sky, every deviation from expected physics, becomes a potential message or a countdown. The universe's secrets might not lie in distant galaxies or quantum foam, but in the invisible architecture of reality itself. And if we're living in someone else's experiment, the greatest discovery wouldn't be that the cosmos is collapsing. It would be that it's meant to. Cosmic inflation is often described as the universe's dramatic growth spurt, a fraction of a second after the Big Bang when space expanded faster than light, smoothing out wrinkles and setting the stage for everything we see today. But what if that explosive beginning wasn't a one-way street? Hidden in the fine print of inflationary theory lies a tantalizing possibility that the same physics-driving expansion might also contain the seeds of its own reversal. Think of inflation like a balloon inflating at breakneck speed. Now imagine that balloon isn't just growing, it's pulsating, with periods of expansion followed by subtle contractions. Some models suggest that quantum fluctuations during inflation could have created bubbles of spacetime where the rules differ. Most of these bubbles would keep expanding, but a fraction might collapse inward, like pockets of a soufflé that rise unevenly and then sink. If true, our observable universe could be one expanding bubble in a vast foam of others, some of which are already contracting. We wouldn't see them, their light could never reach us, but their existence would mean the cosmos is far more dynamic than it appears. The smoking gun for this idea might lie in the cosmic microwave background, the afterglow of the Big Bang. Inflation's fingerprints are all over this radiation, in the form of faint temperature variations that map the early universe's density. But some of those patterns are odd. Certain large-scale anomalies, like the so-called cold spot, defy standard inflationary predictions. Could these be scars from a neighboring bubble universe that collapsed, sending gravitational ripples through our own? It's like finding a crack in a mirror and realizing it wasn't made by you. Something beyond the glass left its mark. Even wilder is the concept of eternal inflation, where new bubbles of spacetime constantly form, each with its own physics. In this multiverse scenario, contraction isn't an end but a transition. A bubble might inflate, spawn new ones, then collapse, recycling its energy into the next cosmic generation. Picture a fireworks display where some sparks flare out while others ignite anew. Except each spark is an entire universe, flickering in and out of existence according to rules we're only beginning to guess. Critics argue this is speculation dressed in equations, but the math is surprisingly robust. The same quantum fields that drove inflation could, under certain conditions, tunnel into lower energy states, triggering localized collapse. It's akin to water freezing into ice. The molecules rearrange and suddenly the rules change. If such a phase transition happened in our cosmic backyard, the effects might already be unfolding, too subtle for current telescopes to catch but inevitable all the same. The real twist: inflationary contraction wouldn't look like the big crunch of old textbooks. Instead of a uniform collapse, it might resemble a cosmic game of dominoes, with regions of space tipping into reversal at different times. Galaxies in one neighborhood could start falling toward each other while the rest of the universe expands merrily along. We might not notice until the first blue-shifted starlight appears, a lone galaxy swimming against the tide, the first herald of a change we never saw coming. For now, these ideas live at the edge of cosmology, where theory outpaces observation. But with next-generation telescopes probing the cosmic microwave background in unprecedented detail, and gravitational wave detectors listening for whispers from the early universe, we might soon have answers. Inflation taught us the cosmos is capable of breathtaking violence and beauty. If it also holds the key to contraction, then the universe's story is far from over. It might just be getting started. Neutrinos are the ghosts of the particle world. Billions pass through your body every second, leaving no trace. These nearly massless particles, born in the hearts of stars and the fury of supernova, barely interact with matter, making them cosmic shadows. But what if these elusive phantoms hold clues to the universe's deepest secret? Their strange behavior, particularly a phenomenon called neutrino oscillation, might be whispering hints about a cosmos not just expanding but quietly contracting. At first glance, neutrinos seem too insignificant to shape the fate of galaxies. They're often called the universe's background noise, a sea of particles so light they were once thought to have no mass at all. Yet experiments like Super Kamiokande and Ice Cube revealed something astonishing. Neutrinos switch identities as they travel, morphing between three flavors: electron, muon, and tau. This chameleon-like trait, known as oscillation, proves they have mass, however tiny, and in the vast scales of the cosmos, even the slightest mass can add up. Trillions of neutrinos, each a featherweight, together could exert a gravitational pull subtle enough to nudge the universe's trajectory over billions of years. Here's where it gets speculative and thrilling. If the universe were contracting, the density of neutrinos would increase as space compresses. More neutrinos in a smaller volume means more frequent interactions, potentially altering how they oscillate. Picture a crowded room where whispers get louder as the walls close in. Similarly, in a collapsing cosmos, neutrino oscillations might amplify, creating detectable patterns in their flavor ratios. Telescopes like the upcoming Deep Underground Neutrino Experiment (DUNE) could spot these anomalies, catching neutrinos behaving in ways that defy expansion-only models. But neutrinos might not just be passive signposts, they could actively participate in the reversal. Some theories suggest that as space contracts, high-energy neutrinos from the early universe could re-emerge, their relics gaining strength in the denser environment. These relic neutrinos might interact with dark matter or dark energy, tipping the balance from expansion to contraction. It's like a hidden lever in the cosmic machinery, one we've overlooked because neutrinos are so hard to catch. The most tantalizing possibility: neutrinos could be entangled with the universe's geometry in ways we're only beginning to understand. In string theory, for instance, neutrinos might vibrate through extra dimensions, sensing changes invisible to us. If those dimensions contract, neutrinos could carry echoes of that shift into our observable universe, their oscillations encoding a message from higher dimensional space. Deciphering that code might require a new kind of physics, one where the smallest particles and the largest structures are intimately linked. For now, neutrino cosmology remains a frontier. But every new detection, every anomaly in the data, could be a breadcrumb leading us toward a startling truth. The universe's fate might not be written in the light of distant supernova or the pull of black holes, but in the silent dance of particles so faint, we've only just learned to see them at all. Dark matter is the universe's invisible scaffolding, an enigmatic substance that doesn't emit light, reflect it, or interact with ordinary matter in any way except through gravity. Yet despite its ghostly nature, its presence is undeniable. Galaxies spin faster than they should. Clusters of galaxies hold together when they ought to fly apart, and the cosmic web stretches across the void in patterns only possible with an unseen hand guiding it. For decades, scientists have assumed dark matter's role was passive, a cosmic glue holding structures together while dark energy drives the universe apart. But what if dark matter isn't just a spectator? What if, given enough time, its relentless gravitational pull could become the engine of a cosmic reversal? The key lies in dark matter's distribution. Unlike ordinary matter, which clumps into stars, planets, and galaxies, dark matter forms vast, diffuse halos that envelop galaxies and stretch between them in sprawling filaments. These halos are far more massive than the visible matter they contain, meaning their gravitational influence is immense and cumulative. Over trillions of years, as dark matter halos continue to grow through mergers and accretion, their combined gravity could begin to counteract dark energy's outward push. It's like a tug of war where one team starts weak but grows stronger with every new recruit. But here's the twist: dark matter might not act alone. Some theories suggest it could interact with itself in ways we don't yet understand, through forces beyond gravity. If dark particles can collide or decay, they might release energy that alters the balance between expansion and contraction. Picture a hidden reservoir of pressure building in the shadows, one that only reveals itself when the universe reaches a tipping point. Certain models even propose that dark matter could undergo phase transitions, sudden shifts in its properties that amplify its gravitational effects, like a stealthy switch flipping in the cosmic basement. The most intriguing clue might lie in galaxy clusters, the universe's most massive structures. Observations show that some clusters are moving in ways that can't be explained by visible matter or standard dark matter models alone. They're being pulled toward something, or perhaps toward each other, with more force than expected. Could this be the first hint of dark matter's hidden agenda? If these clusters are already responding to a larger-scale collapse, their motion might be the earliest tremor of a coming cosmic shift. Yet dark matter's role in contraction isn't just about brute force. Its distribution could create a fractal pattern of collapse, with some regions reversing before others. Imagine a sheet of paper crumpled unevenly. Some folds press inward while others stretch outward. In this scenario, pockets of the universe might begin contracting long before the whole cosmos does, creating islands of implosion in an otherwise expanding sea. We could be floating in one of those islands right now, oblivious to the collapse happening just beyond our observable horizon. The real challenge is proving any of this. Dark matter doesn't announce its intentions. It leaves only gravitational breadcrumbs. Future telescopes mapping the large-scale structure of the universe in unprecedented detail might spot anomalies, unexpected voids, or filaments bending in ways that suggest a hidden current. Particle detectors buried deep underground could catch glimpses of dark matter interactions, revealing whether it's capable of more than we've assumed. And if the universe's expansion rate shows unexpected variations in different directions, it might be the signature of dark matter's gravity starting to win. For now, dark matter remains a mystery wrapped in an enigma. But if it's silently tilting the cosmic scales toward contraction, then the universe's fate isn't just written in the stars, it's hidden in the dark. And the more we learn about this invisible architect, the closer we might get to answering the ultimate question: is the universe truly expanding forever, or is it just biding its time before the great collapse begins? Cosmic voids are the universe's great emptiness, vast deserts of space spanning hundreds of millions of light-years, where galaxies are few and far between. These colossal bubbles of nothingness aren't just accidental gaps. They're active players in the cosmic drama, sculpted by the push and pull of dark energy and gravity. But what if these voids aren't just expanding like the rest of the universe? What if, hidden within their eerie stillness, they're actually the first dominoes to fall in a cosmic reversal? Take the Boötes void, for example, a staggering emptiness so large it could fit thousands of Milky Ways with room to spare. Standard cosmology says voids grow as dark energy pushes galaxies apart, leaving behind ever larger pockets of near vacuum. But some simulations suggest a different possibility. If dark energy's grip weakens, voids could stop stretching and begin collapsing inward, their edges creeping closer as gravity regains the upper hand. It's like watching a sponge decompress in reverse. The holes don't just stop growing, they start closing. The telltale sign would be in the void's motion. Normally, galaxies at the edges of voids drift outward, riding the wave of cosmic expansion. But if contraction were underway, we'd expect to see those galaxies slowing down, stalling, or even reversing course as the void's gravitational pull once negligible, starts to dominate. Astronomers are already hunting for these subtle shifts. By mapping the velocities of galaxies around voids like Boötes, they're looking for anomalies, streams of stars that seem to hesitate or turn back, like fish swimming against a tide they can't yet see. Even stranger is the role of dark matter in voids. These regions aren't entirely empty, they're threaded with faint filaments of dark matter, the universe's invisible scaffolding. If dark matter's density increases as voids contract, its gravitational influence could snowball, accelerating the collapse. Picture a ghostly net tightening around the void, pulling the fabric of space itself inward. The result, voids might shrink faster than expected, their boundaries sharpening into cosmic walls where galaxies pile up like driftwood on a receding shore. But here's the catch: voids don't act alone. They're part of a cosmic web where empty regions balance dense clusters in a delicate equilibrium. If voids collapse, that balance tips. Galaxy clusters, once held apart by the stretching space between them, could begin to feel each other's pull more strongly. The web might start tangling, filaments snapping under the strain as gravity rewires the universe's architecture. We wouldn't see it happen all at once, just a slow motion unraveling, with voids as the first stitch to loosen. The most tantalizing clue might lie in the cosmic microwave background. Light passing through voids gets stretched, creating cold spots in the otherwise uniform glow of the early universe. If voids are contracting, those cold spots could deepen or shift in ways that defy standard models. Future telescopes, like the European Space Agency's Euclid mission, could spot these distortions, turning the CMB into a backlit screen that reveals the void's hidden motions. For now, the voids keep their secrets, but if they're truly the first signposts of contraction, then the universe's fate might not be written in the stars, but in the spaces between them. And as we peer deeper into those emptinesses, we might find they're not so empty after all. The holographic principle turns our understanding of reality inside out, literally. It proposes that everything we perceive in 3 dimensions, stars, galaxies, even our own bodies, might actually be encoded on a distant, 2-dimensional surface, like a cosmic projector screen. Every event, every particle, is just a shadow cast from this underlying boundary. At first glance, this seems like pure science fiction, but the math behind it is startlingly precise, rooted in black hole physics and quantum theory. Now take this dizzying idea and layer it onto the possibility of a contracting universe. Suddenly, the question isn't just whether space is shrinking, it's where that shrinkage is even happening. Picture a balloon deflating. In our everyday experience, it's obvious the rubber is collapsing inward. But if the universe is a hologram, that contraction might not be occurring in the 3D space we see. Instead, the real action could be happening on that hidden 2D surface, with our 3D reality just mirroring the changes like a movie reacting to edits in the film reel. In this view, galaxies aren't being pulled together by gravity in 3 dimensions, they're being rewritten pixel by pixel on a flat boundary we can't perceive. The collapse would be less like objects moving and more like a code being compressed, with the universe's information density increasing as the file size shrinks. This raises a haunting question. If the universe is a hologram, how would contraction even appear to us? Light, time, and space as we know them might be secondary effects, illusions generated by deeper processes. A contracting holographic universe could distort in ways that defy classical physics. Distant galaxies might not just blue shift, they could flicker, pixelate, or even duplicate, like glitches in a simulation running out of memory. The cosmic microwave background, often called the universe's baby picture, might show strange, geometric patterns, artifacts of the 2D code straining under the weight of collapsing dimensions. The holographic principle also redefines entropy in a shrinking cosmos. Normally, we'd expect disorder to decrease as space contracts, like tidying a room by shrinking its walls. But if entropy is tied to information on a 2D boundary, contraction could scramble that data in ways that increase disorder locally, even as the overall system simplifies. It's like shredding a document while the file size shrinks. The individual pieces are chaotic, but the total information is less. This could create bizarre pockets where time's arrow seems to reverse, with stars appearing to unburn or radiation flowing backward in isolated regions. Perhaps the most radical implication is that a holographic universe might not have a single direction of collapse at all. The 2D boundary could fold, twist, or even merge with other holograms, creating a contraction that's patchwork and nonlinear. Some regions might implode while others hover in stasis, like a crumpling piece of paper where some creases deepen faster than others. Observers in different parts of the cosmos could witness entirely different fates, some seeing a universe winding down, others watching it reboot or fracture. For now, the holographic principle remains a theory, albeit one with growing support. Experiments like gravitational wave detectors and quantum entanglement studies might one day uncover hints of that hidden 2D surface. And if they do, it won't just revolutionize our understanding of space, it'll force us to ask whether contraction is even happening in the dimensions we think we know. The universe's grand finale might not be a crunch, a rip, or a freeze, but a rendering error in the deepest code of reality. Time flows forward like an unbreakable rule. Glasses shatter, people age, stars burn out, and we remember the past but never the future. This one-way street is so ingrained in our experience that imagining it reversed feels absurd. But physics doesn't actually forbid time from running backward. The equations governing particles work just as well in reverse, so if the universe began contracting, could time's arrow flip too? The answer lies in entropy, the universe's measure of disorder and its strange relationship with gravity. Entropy is why time feels directional. Think of an ice cube melting in a glass, low entropy when it's solid, high entropy as it disperses into liquid. The process only goes one way because disordered states vastly outnumber ordered ones, but in a collapsing universe, gravity could rewrite these rules. As galaxies and black holes merge, matter gets squeezed into tighter, more organized configurations. Supermassive black holes, for example, are incredibly low entropy objects. Despite their chaos, their gravity packs matter into a tiny volume, effectively cleaning up the universe's mess. If contraction dominates, entropy might not just decrease, it could invert time's arrow entirely, making shattered glasses reassemble and scattered light converge back into stars. But here's the catch: would we notice? Consciousness is bound to entropy's flow. Our brains rely on increasing disorder to form memories and perceive time's passage. If entropy reversed, so would our perception. To an observer inside the collapse, time would still feel forward, with the past seemingly ahead and the future behind. It's like being on a train that switches direction without the passengers realizing the scenery changes, but the experience of movement stays the same. The universe could already be contracting in some regions, with time flowing backward relative to us, and we'd have no way to tell. Causality adds another layer of strangeness. Normally, cause precedes effect. A thrown rock breaks a window, not the other way around. But in a time-reversed region, effects could precede causes, creating closed loops where events bootstrap themselves into existence. Imagine a star's light traveling backward, not from the star to your eye, but from your eye to the star. The math allows it, but the logic breaks our intuition. Some theories suggest quantum entanglement might hold clues particles instantaneously influencing each other across space, could hint at a deeper, time-symmetric reality where past and future aren't so rigidly divided. The most unsettling possibility, time might not reverse uniformly. Just as gravity warps space, it could twist time into localized eddies where arrows point in opposing directions. Black holes, with their extreme gravity, might already host pockets of inverted time, hidden behind their event horizons. If the universe contracts, these eddies could grow, stitching together regions where time flows differently. One civilization might watch galaxies blue shift toward them while another, in a different pocket, sees them redshift away, both convinced their time is the right one. For now, time's arrow remains stubbornly forward. But if the cosmos ever turns inward, the rules we take for granted could unravel in ways we're only beginning to imagine. The universe doesn't owe us consistency. It might just be waiting to flip the hourglass when we least expect it. Right now, galaxies drift apart like ships in an endless ocean, their collisions rare and dramatic events. But in a contracting universe, that ocean would begin to drain, and those ships would have nowhere to go but toward each other. The distance between galaxies, once vast and growing, would shrink relentlessly, turning the cosmos into a crowded dance floor where collisions aren't just inevitable, they're the main event. Picture the Milky Way and Andromeda, already on a collision course set for 4 billion years from now, in an expanding universe that's a distant, isolated spectacle. But if space itself were contracting, such mergers would unfold everywhere and far sooner. Galaxies that should have drifted apart forever would instead be pulled back together by the tightening fabric of reality. The night sky, now a tranquil scattering of stars, could one day blaze with the light of countless galactic pileups, each one igniting bursts of star formation as gas clouds crash together. These wouldn't be slow-motion car crashes. As galaxies merge, their supermassive black holes would spiral toward each other, unleashing gravitational waves powerful enough to ripple across space-time. Stars wouldn't just collide, they'd be hurled into new orbits like pinballs, some ejected into the void while others plunged toward the galactic center, fueling quasars brighter than anything seen today. The resulting starburst galaxies would outshine entire clusters, their furious star birth glowing so intensely they'd be visible across the universe. But here's the eerie part. We might already be witnessing this in distant corners of the cosmos. Some galaxy clusters, like the Bullet Cluster, show signs of violent collisions where dark matter and gas have been wrenched apart. Others, like those in the Phoenix Cluster, exhibit runaway star formation, as if space itself is squeezing them tighter. Could these be hints of localized contraction, regions where dark energy's grip has faltered and gravity is taking over? Or are they just previews of what's to come, snapshots of a future where the entire universe turns into a cosmic demolition derby? The strangest twist, in a contracting cosmos, these collisions wouldn't just reshape galaxies, they'd rewrite the rules. As black holes merge and grow, their combined gravity could dominate entire regions, creating gravitational tides strong enough to warp time itself. Light from new stars born in the chaos might blue shift as space contracts around it, painting the sky in colors we've never seen. And if life exists in those far future galaxies, it would witness a universe utterly alien to ours, one where the heavens don't quiet down, but grow ever louder, ever brighter, until the final, crushing embrace of the Big Crunch. For now, these ideas lie at the edge of speculation. But with every galaxy collision we observe, every anomaly in star formation rates, we're piecing together a puzzle that might one day reveal the universe's true trajectory. The cosmos could be far more dynamic than we've dared to imagine, not just expanding or contracting, but doing both at once, in ways we're only beginning to glimpse. Imagine a civilization thriving in a universe that's no longer expanding but slowly, inexorably collapsing. The first signs might be subtle, stars appearing slightly brighter as their light gets compressed by shrinking space, distant galaxies no longer drifting away but holding eerily still. Over millennia, the changes would accelerate. Temperatures would climb as the cosmic background radiation, once a faint whisper of the Big Bang, gains energy from the contraction, bathing the universe in a growing warmth. The night sky, once a cold expanse of darkness, could one day glow with the heat of a rising thermal tide. For life clinging to existence, the challenges would be unlike anything evolution has ever faced. Survival in such a world would demand radical adaptation. On Earth, organisms have endured extreme conditions, deep-sea vents, frozen tundras, even the vacuum of space. But a contracting universe wouldn't just alter environments. It would rewrite the laws of physics at their core. With space itself collapsing, the very notion of distance would change. Planets might find their orbits tightening, their years shortening as they spiral closer to their stars. Civilizations would need to master energy sources beyond stars, perhaps harvesting the heat of the universe itself as it contracts into a denser, hotter state. Some theories suggest black holes could become the last bastions of energy, their hawking radiation intensifying as the cosmos shrinks around them. But what if adaptation isn't enough? The most daring minds might look beyond survival toward escape. If the universe is contracting, could life flee to another? The idea of a multiverse, once pure speculation, takes on urgent practicality in this scenario. Wormholes, hypothetical tunnels through space-time, might offer a path out if they exist. Quantum physics allows for the possibility of bubble universes, pockets of space-time with their own laws, budding off from our own. A sufficiently advanced civilization might learn to create or navigate these bubbles, seeding life anew in a younger, expanding cosmos. It's a Hail Mary pass against entropy, but in a dying universe, even the slimmest hope demands exploration. Yet the greatest obstacle might not be technological, but existential. Life as we know it is built on the arrow of time, the steady march from past to future. In a contracting universe, entropy could reverse, turning cause and effect into a tangled loop. Memories might unravel, consciousness itself flickering in and out of coherence. Could intelligence persist in a reality where time's flow is no longer guaranteed? The answer might lie in forms of life we can't yet imagine, beings not bound by biology, but by patterns of information woven into the fabric of space-time itself. For now, these questions linger at the edge of science and philosophy, but they remind us that life, in all its stubborn creativity, has always found a way to endure. Whether huddled around the last black holes or stepping through a doorway to another cosmos, the story of life might not end with the universe's contraction. It might just take a turn we can't yet foresee. The cosmos doesn't owe us a gentle finale, but neither does it deny us the chance to write our own. Einstein called it his greatest blunder, a tiny tweak to his equations of general relativity, a fudge factor he added to keep the universe static. The cosmological constant was meant to balance gravity's pull, preventing the cosmos from collapsing under its own weight. When Edwin Hubble discovered the universe was expanding, Einstein tossed the idea aside, dismissing it as unnecessary. But what if that so-called blunder wasn't a mistake at all? What if it was a clue hidden in plain sight, pointing toward a universe that doesn't just expand but could one day contract? The cosmological constant wasn't just a random number. It represented a repulsive force embedded in the fabric of space itself, a kind of anti-gravity pushing against collapse. Today, we know it as the simplest explanation for dark energy, the mysterious force accelerating the universe's expansion. But here's the twist: Einstein's constant wasn't locked into a single value. The math allows it to shift, even flip from positive to negative. If that happened, the repulsion driving galaxies apart could transform into an attraction, pulling everything back together. It's like a pendulum swinging from push to pull, with the universe's fate hanging in the balance. Modern physicists have dusted off Einstein's old equations, reimagining the cosmological constant not as a fixed parameter, but as a dynamic field, one that could evolve over time. Some theories, like quintessence, propose that dark energy isn't constant at all, but a fluid whose density and pressure change as the cosmos ages. Picture a balloon filled with air that thickens or thins unpredictably. If this dark fluid were to condense into a negative pressure state, the universe's expansion could stall, reverse, and begin collapsing. The very force Einstein invented to prevent contraction might, under the right conditions, become its catalyst. Even stranger is the quantum vacuum's role in all this. Empty space isn't truly empty, it's a seething foam of virtual particles popping in and out of existence. This quantum froth generates energy, and according to some calculations, that energy could behave like Einstein's constant. But there's a catch: the predicted value is astronomically larger than what we observe. This cosmological constant problem is one of physics' greatest unsolved puzzles. If the vacuum's energy can vary, or if unknown symmetries cancel it out in ways we don't yet understand, the door opens to a universe where dark energy's strength and even its sign could change. The most tantalizing possibility: evidence might already exist. Astronomers have noticed subtle disagreements in measurements of the universe's expansion rate, a discrepancy known as the Hubble tension. Some researchers speculate this could hint at a cosmological constant in flux, its value shifting imperceptibly over billions of years. Other clues lurk in the large-scale structure of the cosmos, voids between galaxies that seem a little too empty, or filaments of matter clumping in unexpected ways. These anomalies could be the first whispers of a cosmos not just expanding but preparing to turn inward. Einstein might have abandoned his constant, but the idea refuses to die. It's a reminder that even our greatest minds can't always foresee the full implications of their work. The cosmological constant wasn't a blunder, it was a premature revelation, a piece of the puzzle we're only now beginning to fit into place. And if it holds the key to contraction, then the universe's fate might have been written into the equations all along, waiting for us to read between the lines. Quantum entanglement is one of the most baffling phenomena in physics, a ghostly connection that binds particles across unimaginable distances, making them mirror each other's states instantaneously, as if space and time don't apply. Here on Earth, we've seen entangled particles in labs, their spins or polarities perfectly correlated no matter how far apart they are. But what if this strange linkage isn't just a quirk of tiny particles? What if the entire universe is threaded with quantum connections, silently coordinating its behavior on the grandest scale imaginable? Picture the cosmos as a vast, invisible web, where every galaxy, every star, and even the void between them is subtly intertwined through quantum entanglement. Normally, we think of gravity as the universe's great unifier, pulling matter together in a slow cosmic dance. But entanglement could be working behind the scenes, creating a deeper layer of synchronization, one that doesn't rely on force or distance, but on a fundamental unity written into the fabric of reality itself. If dark energy's push ever weakened, these quantum threads might act like hidden puppet strings, guiding the universe's reversal in perfect, instantaneous harmony. The wildest part, entanglement doesn't just link particles, it can scale up. Recent experiments have entangled clouds of atoms, even microscopic diamonds, proving that quantum weirdness isn't confined to the subatomic realm. Now stretch that idea to cosmic proportions. Black holes, those gravitational monsters, might be entangled with each other through their event horizons, their fates intertwined across billions of light years. If one begins collapsing inward, its entangled partner could follow suit, not because of gravity's pull, but because quantum mechanics demands it. The universe wouldn't contract piece by piece, it could flip all at once, like a light switch thrown by an unseen hand. This isn't just speculation. The holographic principle, a radical theory born from black hole physics, suggests that all the information in our 3D universe might be encoded on a 2D boundary at its edge, a cosmic hard drive where entanglement plays the role of data transfer. If that's true, then contraction wouldn't be a physical collapse so much as a rewrite of that underlying code, with entangled bits flipping in unison to pull the universe back toward its origin. Yet the most tantalizing clue might come from the cosmic microwave background. Its faint temperature variations, the echoes of the Big Bang, show patterns that some physicists argue resemble the signatures of quantum entanglement on a universal scale. If those patterns aren't random, if they're the fingerprints of a cosmos born already entangled, then the universe might not just be capable of synchronized reversal. It might have been designed for it, of course. Proving any of this is a monumental challenge. Entanglement is famously fragile, shattered by the slightest interaction with the environment. How could such delicate links survive the chaos of cosmic evolution? The answer might lie in the vacuum of space itself, where particles flit in and out of existence, constantly refreshing their quantum connections. Or perhaps entanglement is more resilient than we think, woven so deeply into space-time that not even the fury of colliding galaxies can sever its bonds. For now, these ideas hover at the edge of theory, where mathematics outpaces observation. But if the universe truly is entangled on a cosmic scale, then its fate might not be decided by gravity or dark energy alone. The Great Reversal could be a quantum symphony playing out in perfect, silent harmony, a finale written into the universe's first notes. The idea of a multiverse stretches our imagination beyond a single cosmos, suggesting countless universes bubbling into existence, each with its own laws of physics and fate. Some might expand endlessly, others collapse in fiery crunches, and a few could oscillate between the two like cosmic pendulums. If this is true, then our universe's apparent expansion might just be a local phenomenon, one thread in a tapestry of realities where contraction is just as common. Imagine a foam of soap bubbles, some growing, some popping, and others shrinking quietly in the background. Our bubble happens to be inflating, but right next door, another universe could be collapsing in on itself, its galaxies rushing toward a shared doom we'll never see. The multiverse isn't just science fiction, it's a serious contender in theoretical physics, emerging naturally from theories like inflation and string theory. Eternal inflation, for example, suggests that new universes are constantly budding off from a larger, ever-expanding space-time. Most of these baby universes would inflate and cool, forming stars and galaxies like ours. But some might hit a quantum snag, their inflationary energy faltering early, leaving them vulnerable to gravitational collapse. In this view, contraction isn't an anomaly. It's just one possible outcome in a cosmic lottery where the odds are stacked by random fluctuations in energy fields. String theory takes this further, proposing a multiverse where each universe occupies a different brane, short for membrane, floating in higher dimensional space. These branes could collide, merge, or even recoil after expansion, like rubber sheets snapping back after being stretched. If our brain is expanding, another might be contracting right beside us, separated by dimensions we can't perceive. The eerie part, gravitational waves from a neighboring brain's collapse might leak into our universe, leaving faint imprints in the cosmic microwave background, ghostly whispers from a reality where the sky is falling. But how would we ever know? If other universes are truly disconnected, their contraction would leave no trace in our telescopes. Yet some physicists speculate that anomalies in our own cosmos, regions where gravity seems slightly stronger, or where dark energy's effects weaken, could be shadows of a nearby universe's implosion. It's like hearing muffled thumps through a wall. You can't see the source, but you know something's happening on the other side. Future experiments, like ultra-precise measurements of the cosmic microwave background or gravitational wave detectors tuned to exotic frequencies, might one day catch these echoes. The most mind-bending possibility, contraction in one universe could trigger expansion in another. Imagine two brains connected by a quantum thread. One collapses, releasing energy that inflates its neighbor like a cosmic seesaw. Our universe's Big Bang might have been someone else's Big Crunch, a recycling of space-time we're only now beginning to fathom. If true, then the multiverse isn't just a collection of isolated worlds, but a dynamic network where birth and death are intertwined, each universe's fate written in the collapse of another. For now, these ideas live at the frontier of cosmology, where theory outpaces proof. But they force us to ask, is our universe's expansion the rule, or just an exception in a grander scheme? If the multiverse is real, then contraction isn't a catastrophe, it's just another note in an endless cosmic symphony, playing variations we're only beginning to hear. NASA, a next generation of space telescopes and gravitational wave detectors, might be the first to catch whispers of a universe quietly collapsing. While today's instruments map the cosmos in broad strokes, tomorrow's missions are designed to listen for subtler disturbances, anomalies that could betray a hidden reversal. Take the Laser Interferometer Space Antenna, or LISA, set to launch in the 2030s. Unlike Earth-bound observatories, this space-based detector will float in formation, spanning millions of kilometers to catch low-frequency ripples in space-time. Gravitational waves from merging supermassive black holes are its primary target, but there's a tantalizing secondary possibility. If the universe is contracting, even slightly, the wavelengths of these waves could stretch or compress in unexpected ways as they traverse shrinking space. LISA's unprecedented sensitivity might spot these distortions, like hearing a song played just a half-step out of tune, a faint but telling clue that the cosmos isn't expanding as we thought. Then there's the Nancy Grace Roman Space Telescope, poised to launch later this decade. While Hubble and James Webb focus on deep-field imaging, Roman will conduct wide-field surveys, mapping the distribution of galaxies and dark matter with unmatched precision. Its true power lies in spotting deviations from the expected cosmic expansion. If certain regions of the universe show peculiar motions, galaxies drifting toward each other faster than gravity alone can explain, it could signal localized contraction. Roman's infrared eyes might also catch strange shifts in the brightness of distant supernova. In an expanding universe, these stellar explosions dim predictably with distance. But if space is contracting, their light could appear subtly brighter, squeezed by the tightening fabric of reality. Even a handful of these outliers could force a radical rethink of dark energy's role. But the real game-changer could come from the European Space Agency's Euclid mission, already scanning the sky for traces of dark matter and dark energy. Euclid's detailed 3D maps of galaxy positions and shapes might reveal something even more startling: large-scale structures bending in ways that defy standard expansion models. Imagine a cosmic web where filaments of galaxies don't just stretch, they warp, as if tugged by invisible currents. This could hint at gravitational imbalances caused by dark energy weakening in certain areas, allowing contraction to take hold. Euclid's data, combined with Roman's, might paint a picture of a universe not uniformly expanding, but folding in on itself in patches, like a crumpled sheet of paper. The wild card in all this, the Square Kilometre Array, the world's largest radio telescope, now under construction. By tracking hydrogen gas in the early universe with exquisite precision, it could uncover anomalies in the rate of expansion over cosmic time. If dark energy's strength has fluctuated or even flipped, the SKA's ultra-sensitive measurements might catch the inflection point, the moment the universe's acceleration began to slow. It's like finding a fossilized footprint in the mud. The shape of that curve could tell us whether the cosmos is coasting, braking, or preparing to reverse course. These missions share a common thread. They're not just looking for confirmation of what we already know, but for the cracks in our understanding. Every anomaly, every statistical glitch could be the first hint of a cosmic U-turn. And while none of these telescopes were designed specifically to hunt for contraction, their unprecedented precision turns them into cosmic eavesdroppers, listening for the universe's quietest secrets. The next decade of astronomy won't just deepen our knowledge, it might shatter it entirely, revealing a cosmos far stranger, far more dynamic than we've ever dared to imagine. When people hear the universe is contracting, they often picture a sudden, catastrophic crunch, like a soda can being crushed in an instant. But the reality is far slower, far stranger. A cosmic reversal wouldn't be a single event. It would unfold over billions of years, a gradual tightening so subtle that entire civilizations could rise and fall without noticing. Think of it like the universe taking a deep breath in after centuries of exhaling, a slow, almost imperceptible shift in the fabric of reality itself. One of the biggest myths is that contraction would mean everything rushing toward a single point, like a rewinding film reel. In truth, gravity isn't that uniform. Galaxies wouldn't just reverse course in perfect sync. Some might stall first, others drift sideways, like leaves caught in a slow-motion whirlpool. Even as space itself contracts, the sheer vastness of the cosmos means local forces, black holes, dark matter halos, even the momentum of galaxies would create pockets of chaos. Picture a crowd dispersing after a concert, only for the exits to start narrowing. Some people would push forward, others shuffle aimlessly, and a few might not realize the walls are closing in at all. Another misconception, that contraction would feel violent or disruptive. In reality, the forces at play are so colossal, so evenly distributed, that the experience would be eerily smooth. Light from distant stars might blueshift over millennia, growing imperceptibly brighter, but to anyone living through it, the change would be invisible without precise instruments. Temperatures would rise as the cosmic microwave background, the afterglow of the Big Bang, gains energy from the shrinking space, but this, too, would happen over timescales dwarfing human history. The universe wouldn't crash, it would simply pivot, its expansion slowing, stalling, then reversing with the quiet inevitability of a tide turning. Then there's the fear that contraction spells instant doom, but collapse doesn't necessarily mean destruction, it could mean transformation. Stars might burn hotter and faster in a denser cosmos, their lifespans shortening but their light intensifying. Galaxies, drawn closer, could ignite new waves of star formation, turning the night sky into a fireworks display of colliding nebulae. Even black holes, those cosmic vacuum cleaners, might find new purpose, merging into gargantuan structures that anchor the universe's next act. The end of expansion wouldn't be an ending at all, just a new, unfamiliar chapter. the most persistent myth that we'd see it coming. In truth, by the time the universe's contraction became obvious, it might already be unstoppable. Light from distant galaxies takes so long to reach us that we're always peering into the past. If the cosmos began collapsing today, the light showing that reversal wouldn't arrive for millions or even billions of years. We could be living in the early stages of contraction right now, with the evidence still en route across the void. It's like standing on a beach, watching waves roll in, unaware that the tide has already turned miles out at sea. The universe doesn't owe us drama. Its grandest shifts are often its quietest, playing out in wavelengths and velocities too subtle for human scales. Contraction wouldn't be a catastrophe, it would be a slow dance, one where the music changes so gradually, no one notices until the rhythm is already new. And that might be the most humbling truth of all. The cosmos doesn't collapse with a bang, but with a whisper. If the universe is truly destined to contract, collapsing inward over billions of years, humanity faces a dilemma unlike any other. This isn't just about survival, it's about meaning. How do we reconcile our fleeting existence with a cosmos that might one day erase every trace of us? The ethical weight of that question presses down like gravity itself. Do we resign ourselves to oblivion, or do we fight against the dying of the light with every tool and idea at our disposal? Consider the long-term planning required. Most civilizations measure their futures in decades or centuries, but cosmic contraction demands thinking on scales that dwarf recorded history. Projects like Dyson spheres or interstellar arcs, once the stuff of science fiction, become urgent priorities in a universe with an expiration date. The challenge isn't just technological, it's psychological. Can a species wired for short-term survival rewire itself to plant trees whose shade it will never enjoy? The answer might lie in stories, not just equations. Cultures that pass down knowledge through myths and rituals could outlast those that rely solely on hard drives vulnerable to cosmic decay. Yet even the most ambitious engineering raises ethical quandaries. If resources grow scarce as space contracts, who decides which civilizations get to flee collapsing regions? Will humanity become cosmic nomads, stripping planets bare to fuel our escape, or stewards preserving what little remains? The choice between selfishness and solidarity won't just define our legacy, it could determine whether intelligence itself persists long enough to witness the universe's final act. Philosophically, contraction forces us to confront the value of impermanence. If all things must end, does that render our struggles meaningless? Or does it make every act of creation, every moment of connection, more precious? The ancient Stoics found freedom in accepting fate while striving for virtue. In a shrinking cosmos, their wisdom takes on new urgency. We cannot control the universe's trajectory, but we can choose how we meet it with despair or with defiant curiosity. Perhaps the greatest ethical test isn't survival, but stewardship. Even as the heavens close in, we might still etch our mark not in stone, but in space-time itself. Theories suggest advanced civilizations could encode information in gravitational waves or black hole spins, leaving messages for whatever or whoever comes next. In the end, the universe may forget us, but that doesn't mean we have to go quietly. While the idea of a contracting universe might sound like fringe science, it's gaining serious traction in academic circles, with respected physicists publishing peer-reviewed papers and challenging long-held assumptions. At the forefront is Dr. Anna Agers, a cosmologist at New York University, whose work on bouncing cosmology suggests the Big Bang might not have been a beginning, but a rebound from a previous collapse. Her models, published in Physical Review letters, show how quantum corrections to Einstein's equations could allow space to contract without reaching infinite density, effectively bouncing like a ball compressed to its limit. Meanwhile, at Oxford, Dr. Job Feldbrug and his team are running supercomputer simulations where dark energy's strength fluctuates, revealing scenarios where patches of the universe reverse expansion while the rest marches onward. Their findings, hotly debated at last year's International Conference on Gravitation, suggest contraction might not be all or nothing. It could happen piecemeal, like a quilt slowly stitching itself back together. Experimentalists aren't just theorizing, they're hunting for proof. The Dark Energy Survey, analyzing light from over 300 million galaxies, recently flagged anomalous clusters moving with peculiar coherence, as if tugged by invisible currents. Some researchers argue this could hint at early-stage contraction in our cosmic neighborhood, though skeptics counter that statistical noise is the likelier culprit. More provocative still is work from the Perimeter Institute, where physicists are re-examining the cosmic microwave background's infamous cold spot, a bizarrely frigid region spanning billions of light years. Their controversial preprint suggests it might be a bruise from a pre-Big Bang collapse, an echo of a universe that came before ours. The debate gets even livelier when quantum gravity enters the picture. At UC Berkeley, Dr. Yasunori Nomura's team merges string theory with cosmic contraction models, proposing that extra dimensions could be shrinking independently of our observable space. Their calculations predict subtle shifts in gravitational wave frequencies that future observatories like LISA might detect, like hearing a distant drumbeat change rhythm as the drum itself tightens. Across the Atlantic, CERN theorists are exploring whether high-energy particle collisions could momentarily recreate conditions akin to a contracting universe's energy density, offering lab-scale hints of how matter behaves under reversal. Not everyone's convinced, of course. Establishment heavyweights like Nobel laureate Adam Rees argue that existing expansion data remains airtight, and that contraction theories rely too heavily on untestable assumptions. But even skeptics admit the questions raised are worth pursuing, because if there's one thing cosmology has taught us, it's that the universe thrives on proving us wrong. As datasets grow and telescopes sharpen their gaze, what seems radical today might be textbook tomorrow. The greatest discoveries often begin as heresies. Let's hit pause for a moment and step into a thought experiment. If tomorrow astronomers announced undeniable proof the universe had begun contracting, not in some distant future but now, how would you react? Would you scour the sky for blue-shifting galaxies, calculating how many generations until the stars grow uncomfortably close? Or would you shrug, trusting that billions of years is someone else's problem? This isn't just hypothetical, it's a lens to examine our place in the cosmos. Imagine you're a scientist in this scenario. Your life's work suddenly pivots from studying expansion to decoding collapse. Do you chase the anomalies, those galaxies drifting off script, the cosmic microwave background's odd fluctuations, or do you tear up the old models and start fresh? There's no playbook for this. Every telescope, every satellite becomes a detective scanning for clues in a mystery where the stakes are literally universal. Now shift gears, you're a policymaker, resources are finite and the timeline is murky. Do you greenlight interstellar arc projects, betting on humanity's survival among the stars? Or do you double down on Earth, building underground vaults to outlast the rising temperatures of a shrinking cosmos? The ethics here are staggering. Who gets a seat on the lifeboat? Do we prioritize artists, engineers, children, or lottery winners? And what happens to the billions left behind? Here's a darker twist. What if contraction isn't gradual but accelerating, a cosmic countdown measured in centuries, not eons? Suddenly, philosophy collides with urgency. Do we spend our final days preserving knowledge, etching humanity's story into diamond plates destined for black holes? Or do we embrace hedonism, chasing experiences until the sky itself begins to crumble? There's no right answer, only a mirror held up to our values. Now turn the question outward. If alien civilizations exist, are they facing the same reckoning? Would a contracting universe force cooperation among species, uniting us against the void? Or would it spark desperation, a free-for-all for the last habitable planets? The Fermi paradox, the eerie silence of the cosmos, might find new explanations. Maybe advanced civilizations don't vanish because they self-destruct, but because they're too busy fleeing the collapse. This isn't just speculation, it's a stress test for humanity's imagination. The universe doesn't owe us forever, but it does offer us this moment to wonder, to argue, to dream. So tell me in the comments, if the great reversal began today, what's your move? Do you fight the tide or learn to swim in a shrinking sea? The answer says less about the cosmos and more about us. From dark energies shifting tides to black holes silently weaving the fabric of space, we've ventured into the cosmos's most tantalizing what if, a universe not expanding toward oblivion, but folding inward in a grand, invisible reversal. This isn't just about rewriting textbooks, it's about confronting the humbling truth that the cosmos might be playing a game of cosmic sleight of hand, hiding its true trajectory in plain sight. Every anomaly in distant starlight, every whisper of gravitational waves, every unexplained tug on galaxy clusters could be a breadcrumb leading us toward a revelation that the universe's story is far from linear. It might be cyclical, chaotic, or something beyond our current imagination. The beauty of this idea isn't just in its audacity, it's in how it forces us to question the very foundations of what we think we know. For centuries, we've assumed the cosmos was on a one-way journey, racing outward from the Big Bang toward an uncertain fate. But what if that's only half the picture? What if the universe is breathing, expanding and contracting like lungs in the dark, its rhythms too vast for any single civilization to witness in full? The great reversal might remain theoretical for now, but the questions it raises are immediate and profound. They remind us that science isn't about clinging to dogma, it's about chasing the anomalies, the outliers, the data points that don't quite fit. And that's where you come in. Every time you gaze up at the night sky, every time you ponder the mysteries of dark energy or the enigma of black holes, you're part of this grand investigation. The universe doesn't reveal its secrets easily, but with curiosity as our compass, we're always inching closer. So if these cosmic riddles ignite your imagination, join the conversation. Hit like if you're as captivated by these possibilities as we are. Subscribe to keep exploring the frontiers of space and time, and drop your wildest theories in the comments. Is the universe truly contracting? Are we on the brink of a paradigm shift, or is the cosmos still holding its greatest surprises close? The answers are out there, and together we might just be the ones to find